Welcome to another unit in this workbook, Statistics. This time I'm going to talk about probability theory. Well, if we talk about probability theory, the first thing we can discuss is what is actually probability. Well, for this we could go back to the definition of Laplace, who said, well, the probability of at random finding an event of interest A is simply the number of events of interest divided by all possible events. Well, that's a relatively easy and straightforward definition. This has the big advantage. This actually uses all the insights we gained from set theory, so we can determine a lot of other properties of our definition of probability by simply using the insights we have gained in the context of discussing set theory. And well, what we also know is sometimes referred to as the Kolmogorov axioms, so general true statements about the probability. The first one being the probability always has to be larger or equal to 0. So it's not possible to get a negative probability. Well, it also makes sense because negative probability would mean we would have a negative number of events, which is not possible. We also know that the probability for the insured event, for the event this will happen in any case, is 1. So this also tells us that the probability will always be somewhere between 0 and 1. 0, it's not possible at all. 1, it's 100% possible, so it will happen for sure. And, well, we can actually split up a given property, and, well, the sum of all partial probabilities, if those sets are disjunct, so if there is no intersection between any two of these sets, is equal to taking the union of all sets and then calculating the probability. Well, from a set theoretical point of view, this makes perfect sense, but this actually means that we, in this case, can actually add up probabilities if the events are not related in any which way. Well, that's more or less the short introduction about probability, what is this, and the general properties of probabilities. So now we can actually go on with certain rules, theorems about the use of probability. The first one we can talk about is the so-called conditional probability. Conditional probability means it's a probability of an event A happening under the condition that the event B already has happened. We might add, and that A and B in one way or another are related. If they're not related, then the conditional probability is the same as the unconditional one. So here it makes only sense if those two are related in one way or another. So that's actually what is written here. It's the probability that event A occurs under the assumption that event B already occurred. And that's actually the difference between the conditional probability and this probability. This is the probability that A and B already happened. That's why the conditional probability is one step before all of this. So we can imagine this, and that's why I use this graph here, like walking from the left to the right. Here we have event A. Then the first thing which could be is that, event A actually takes place. Then all the other probabilities following after this are under the condition that event A already happened. Could then be, if we consider the next event B, that this also takes place, then we're up here, or that event B does not take place, then we're down here. So if we actually want to get to this point here, we first have to go along this line, and then we have to go along that line. So the probability that A and B happened is nothing else than the probability that A happened times the probability that B happens conditioned that A already took place. So this times this gives this. This holds for all the other values as well. That's actually the step I illustrated here. However, we can also determine something else. Those two taken together give 100%. Those two taken together are related as well to what happened before. Finally, those four are all four possible outcomes, so they added up give 100%, so 1 as well. That was the first law we are talking about, or the first definition we talked about. The second one is the so-called law of total probability. That's if we have an event space, so we have a set of events that could take place, and this event space can be split up into pairwise disjunct subsets. So in other words, those subsets BI, they do not overlap, but they fully cover the event space omega. So there's no event which is not part of any of the BIs, and there's not one element in one of the BIs which is an element in any of the other BIs. If this holds true, then, well, in the easiest way, we could say that this probability here holds as well, that A is simply the combination of the two probabilities which we have here, which, if we consider our definition of the conditional probability from the last slide, is simply the probability that A and B happened, that A and not B happened. So in this case, we're getting rid of the B in this case. Well, that's the easiest version. If we just have two possible outcomes for B happening, B not happening. In general, if we have something like this, more subsets, then we could write this down in the following fashion. Well, looks similar to what we have here, B1, B2, then there would be more terms, and A always conditioned to any of these B's. So in other words, once we get rid of all the disjunct B's, then we are getting back to the total absolute probability, which is of interest to us. So that's a neat way. However, there's also different other way to think about the total probability. And well, we said there are disjunct subsets which make up the event space omega. So in other words, those BI, or the probability of BI happening, if I take all of them, they add up to 100%. So they are like weights. Weights of the conditional probabilities. So in other words, the law of total probability is nothing else than the weighted average of all the conditional probabilities. A slightly different way of thinking about this, but for some people this actually makes a bit more sense than just going to consider this as the probability of A and B happening, of A and B complement happening. Well, that was the law of total probability. So we have one more to go with. That's the so-called theorem of Bayes. Again, we consider that our event space is made up of pairwise disjunct subsets BI, which make up the whole event space. Then we could say, that's the easiest version, that these two probabilities are the same as those two, which actually makes sense, because if I multiply those two, what I will get is the probability that A and B occur, so it's A intersected B. If I calculate this part, that's the probability of B intersecting A. Well, A intersecting B and B intersecting A are exactly the same things. That's because the intersection works like a plus sign, and there we can, well, in either case, go with A intersects B or B intersects A. Or in other words, more mathematical speak, it's a commutative operation. So that's how this easy version holds. Both sides result in the same outcome. But we can also use a slightly more sophisticated version by first off solving for this part here and then rewriting the probability of A with what we had from the slide before, this part here, for the total probability. Well, if we can use this version where we just work with B and the complement of B, we can also do this in the very general version with this part where we have down here the general version of the law of total probability. Well, we could talk quite a long time of what the theorem of Bayes actually stands for, what the advantages of using this law actually are, or this theorem actually are. I would, however, in the context of this book and where you mostly find this in introductory statistics, mention the comment that it's quite often being used if you just want to switch probability and condition around. So here we see we're looking for BK under the condition A. We already know A under the condition BK. So if it's about switching condition and what we're looking for as a probability, then you could also use the theorem of Bayes. But well, as I said, there's a lot of other things this is good for, it can be used for, but we do not have the time here to go in all the details. So that's more or less then everything I wanted to mention as the main rules, main definitions in the context of probability theory, which are of interest to us. So I hope you enjoyed it. I say goodbye and see you next time.